The, the research paper that we are going to discuss today is called MovieGen, a cast of media foundation models. Behind this paper is actually some remarkable work, obviously, uh, and some very good demos that Meta, the research group, the FAIR research group, has posted in Meta. So I'll start with this. I suppose let's start with the results first. Now, if you look at this particular video, it's a generated movie. Notice how it is a high resolution movie. It looks quite realistic. And amongst other things, notice that it seems to respect the physics quite well, the reflections and things like that, the water reflections, etc., and the waves quite well. And that is a remarkable thing. Now, we do know there has been prior developments like Sora, etc. What these folks will claim and do claim is that they are achieving state-of-the-art results that actually outdoes Sora and other commercial offerings. It's very, very remarkable. Now, let us see what is remarkable about this video generation. Look at this. This is an example of going straight from a prompt to a movie. The text input summary is, a girl is running across a beach and holding a kite. She is wearing jean shorts and a yellow t-shirt. The sun is shining down. Now, usually, I suppose the reason to put this video as one of the first showcase videos is it's hard to get the dynamics of running right. Whenever you do generated videos, it was a tough problem to get the movements right and to get it over a sustained period of time and to get it in high resolution. It is a little bit hard problem technically. And as you can see, they seem to have gotten it right. Amongst other things, observe, which is not quite easy to observe, but as she runs, her feet are leaving footprints in the sand, and you can see it make footprints. You can see the wave of the kite, and it's very natural. It's very, it does respect the physics, and it looks very realistic, in other words. This is a slightly different example. Here, you have given two prompts. You have given a picture of a person, and you have given, with that picture, you have given a text prompt. A woman is sitting on the grass of a pumpkin patch. She is wearing a scarf and holding a cup. The background is filled with rows of pumpkin. I will let you soak this in to realize that there was basically, it is grounded on not only the text prompt, but also an image. And from just one image, it has created this high resolution, high definition video. And to me, it looks very, very realistic. Right? Can anybody spot an obvious error in this video? I couldn't. So obviously, this model that we are going to read about has made quite some strides, as we will see. The next one illustrates that you can not only create video, and it is not just video frames, but it is also learned sound that goes with specifically the word people use is diegetic sound, diegetic ambient sound, and we'll see that. So I'll let So this has come from just a simple text input. Thunder cracks loudly with an orchestral music track. Would you agree that it does seem to honor that? very well. And look at the photorealism of the landscape. You might say that if you look very closely, um, does look a little bit artificial, perhaps. But this is a very interesting image. Here you're grounding it in not an image and a text, but in a video and a text. You give it a video, which is on the left-hand side, and you give it a text and say, transform the lantern into a bubble that soars into the air. So you have a lantern soaring into the air, and it converts into the bubble. Now, I will let you observe something remarkable about this bubble. Look at the way it respects the physics. Do you see that in the bubble is reflected the scene around it? Do you see the reflection of the surrounding scene that is around in the bubble? It's very, very remarkable, actually, that a machine can understand it so well. Then you can generate videos from text. This video is just pure video generation. A sloth with pink sunglasses lays on a donut float in a pool. The sloth is holding a tropical drink. The world is tropical. The sunlight casts a shadow. This is actually a pretty tough video to get right, because you have to get the physics of the waves, the reflection, the light reflection, the cloud, the movement of the cloud. Now, if you notice that as the cloud comes, if you look into the reflections here, it casts shadows not only on the sloth, but on the reflection along with it, in the pool along with it. So there's a lot of real world realism in the video generation. This is even more remarkable. This is the input text is a prompt is the camera is behind a man. The man is shirtless, wearing a green cloth around his waist. He is barefoot, with a fiery object in each hand. He creates wide circular motions. A calm seas in the background. The atmosphere is mesmerizing with the fire dance. Now, two things to notice. First, actually, that he is, I mean, it does respect what the prompt says. But more remarkably, look at the way the fire is dancing and the way it is casting light on this person, in particular on his clothes. And then look at the way the light is casting a variable illumination on the sand. Do you see that? Right? And it's quite remarkable that it can get it right this far. Unless you look very carefully, and I tried to look carefully to see exactly what it didn't get right. The only one that I felt where there was a little bit of artificiality was perhaps the lightning one, where the mountains looked a little bit too perfect. So, text input summary. Now, this is again a beautiful one. A fluffy koala bear surfs. It has gray and white coat and a round nose. The surfboard is yellow. The koala bear is holding onto the surfboard with his paws. The koala bear's facial expression is focused. The sun is shining. This is a very dynamic scene. There's a lot happening here. Both of these scenes, the light and this. And you realize that even in such a dynamic scene, it seems to be getting it right quite well. And also getting the physics and the orientation right, which is quite remarkable. Now, so each of these pictures, I suppose, is trying to bring about a technical point. If you look at this one, there's a text input saying a ghost in white bedsheet faces a mirror. The ghost reflection can be seen in the mirror. The ghost is in a dusty attic filled with oil beams, cloth covered furniture. The attic is reflected in the mirror. The light is cool and natural. The ghost dances in front of the mirror. By the way, do you see that in the mirror, if you look carefully, you can see occasionally a bit of the bedsheet showing up. So obviously a lot of photorealism here. This is another one. Look at the level of details that you can see on the monkey's face, a red monkey playing with a toy ship, the water. You can see the ripples, the way you can see the reflection. And this is actually one of the most remarkable videos that brings out the strength of this model. Right? So I won't do more of it, just one or two more. This one is quite remarkable. I believe this is the last, this one. What it says is that you can give an original video, you can do video editing. Right? Now, if you have been into a video production, you know that video editing takes forever. You want to change the color of somebody's shirt or do something. And people, first of all, it takes a lot of expertise to become good with, I don't know, Adobe Premiere or DaVinci Resolve or something like that. And then to know how and what to do to change the color, the color tone, etc., realistically, or to bring in artificial, some other backgrounds and so forth. But look how easy it is here. You just give it a text input and you say to the original video of a person running, what to me looks something like a Death Valley, or I don't know, scene, some sort of a plain valley. In that thing, you are saying, add blue pom-poms to his hand. And sure enough, now you see the person is carrying a blue pom-pom. What is more remarkable is this one, the lower one. You say, change the landscape, the background landscape, to be that of a cactus desert. I suppose you have transplanted the runner from California to Arizona. So there it is. A cactus desert. Now, if you do know Arizona, you know that it's close to, it's one of the mountain regions. So you can even see mountains, those dry mountains. And then to have fun, it says replace the running clothes with an inflatable dinosaur costume, and it has done that too. So the fact that you can do photo editing, what it means is you realize what it means. If you're a videographer, you would start salivating and wondering, okay, when can I have these features built into the video editing tool, the Adobe Premiere or the DaVinci Resolve? How soon can I have it as built-in feature? It will take a while, I suppose, for it to get polished up and properly viewed, but it's still nevertheless quite remarkable. Look at the original video of somebody wearing virtual reality goggles, and you're saying, change the virtual reality to binoculars or remove the headset altogether. And this one I find quite remarkable. From this video where you can't see the face, it seems to have inferred a pretty good, plausible face, isn't it, to the person, right? And so forth. Another one is like this. This is where you are changing the background in different ways. Now, if you notice, one thing you may notice that when you add fire sparkles to his hand, notice that when the fire comes in front, you can see illumination on his arms from the fire. So it's very realistic. What it means is that whatever the machine has understood, the model has understood, somehow it has understood the nature of the physical world, the physics of the physical world. It's very remarkable, right? From the videos, it has actually figured out of how it is when there's fire, that you will see it illuminating things around it. And I'm almost done, I suppose, but it's worth showing original video, obviously, of a puppy. And now you have the puppy in all sorts of interesting variations. Then likewise, you have this. And this, of course, you have to have penguins. So here we are with penguins, dress the penguin in Victorian outfits. And so you see the penguin and in Victorian clothes and so forth. Lastly comes a very interesting video. You have one picture of this person. You ground the picture and you ground a text input. A man is doing scientific experiments in a lab, etc., etc. And see, from this video, from this picture, you create this video. So guys, do you realize that you're looking at something most remarkable? It is obviously the first question in the first few moments, you're absolutely exhilarated. After a little while, you start worrying at the potential for abuse also, right? So now, if I have your picture, and surely I have, if I want your picture, all I have to do is Google it up. Okay? Then I can create a video of you doing whatever I want to show that you are doing, right? And this might have major law enforcement implications, because now what does it do to video testimony? And it's one of those, in our AI community, of course, this is one of the rising concerns of deepfakes. Um, what exactly, what if anything, should be the law and the regulation to prevent abuse? I think that's still an ongoing conversation, and people are still figuring it out. Look at this. This is pretty realistic given this picture and this person. How many of you can tell that this, I mean, I wouldn't be able to tell that this video is not a real video. And likewise for the dog, and this, and this. So here we go. You could do all sorts of things, produce very personalized videos. Great. You could also produce soundtracks. So for example, rain pours against the cliff and the person with music playing in the background. So So one of the things you will see in this paper, they talk about that if you just give it a video, it will be able to figure out what is the appropriate sound that goes with it. And see, look at this. So I'll do that. And finally, I suppose this is the last demo. So as you can see, it generates two kinds of sounds. One is the sound that would be sort of um, built in from the environment, and the other is sort of the music that video producers tend to give to such, what would be the appropriate sort of play in the background for situations like that, and they tend to do that too. And for example, look at this. So anyway, that's that. Now let's look at the paper. This paper is actually remarkably simple. So I'll talk about the method they use, and what they don't mention is something surprise is the approach, which is simple and a bit surprising. So let's start now with the paper reading of this. So we present MovieGen, the abstract says, a cast of foundation models. I suppose that's a play on words. Movies have casts. So we present MovieGen, a cast of foundation models that generates high quality 1080p HD videos with different aspect ratios and synchronized audio. We also show additional capabilities such as precise instruction-based video editing and generation of personalized videos based on a user's image. So we saw all of that. Our models set a new state-of-the-art on multiple tasks, and this is really worth pointing out. Our model sets a new state-of-the-art. Now, there's a little bit of a background. See, guys, when you look at video editing or video generation, there are many companies who are dedicatedly, commercial companies that are very much into the forefront of video generation. Facebook or Meta, they were not known to be big players in this landscape. They are there. I suppose they were coming up with something. But this is a remarkable thing, that they come out with a model that puts them into the state-of-the-art category. It puts them really at the top. So our largest video generation model is 30 billion parameter transformer trained with a maximum context length of 73K video tokens, corresponding to a generated video of 16 seconds at 16 frames per second. 16 frames per second is understandable. They're saying that they can create videos of up to 16 seconds, which is quite remarkable. These are fairly long video sequences, and certainly usable for, if nothing else, indie video productions. We show multiple technical innovations and simplifications on the architecture, the latent spaces, training objectives and recipes, the data curation, evaluation protocols, parallelization technique, and inference optimizations that allow us to reap the benefit of scaling pre-trained data, model size, and training compute for large-scale media generation. Wow, long sentence. Huh? So we will talk about it. So they have actually, you'll see that there's a whole host of innovations that has taken them there. This is a Herculean effort, a big effort, and not only a big effort, the amount of hardware that it took was astoundingly large. So they have innovation, let's just speak. So now, if those of you who are familiar with Facebook, Meta's research, the FAIR group, a lot of their multimodal work, they often have used the concept that it is far better to understand or bring understanding, induce understanding by using a latent space. If you remember the JEPA series of papers, they and then of course Jan LeCun's position paper and many of this, a lot of which we have studied. So I was sort of looking out that will the latent space representations fare big in this paper too? And sure enough, that's where most of the magic happens. I won't read the rest of the intro, but let's read this. Imagine a blue emu swimming through the ocean. Humans have the astonishing ability to imagine such a fictional scene in great detail. So the moment you say, you just give to another human being, you give a prompt. Imagine a blue emu swimming through the ocean. And obviously the other person goes vivid imagination and will come up with something. That's what they're saying. Human imagination requires the ability to compose and predict various facets of the world. Simply imagining a scene requires composing different concepts while predicting realistic properties about motion, scene, physics, geometry, and audio. And I thought this sentence is really important because it does contain something very crucial in the way they go about it. Simply imagining a scene requires composing different concepts while predicting realistic properties about motion, scene, physics. You have in your mind spontaneously comes this picture. And that picture more or less respects geometry, physics, and everything, right? Equipping AI systems with such generative, compositional, and prediction capabilities is a core scientific challenge with broad applications. While large language models, LLMs, aim to learn such capabilities with the text output space, in this paper, we focus on media, image, video, audio as the output space. So they're saying just like LLMs produce text, we directly imagine a set of models whose output space is multimedia. Right? We present MovieGen, a cast of media generation foundation models. MovieGen models can natively generate high fidelity images, video, audio, while, etc. Now we do, I mean, these things we have seen already in the demonstration. So I'll rush past this. Now the crucial statement is, how do we do that? This is the crucial thing. We find that scaling the training data, compute and model parameters of a simple transformer-based model. So what are we referring to in the first sentence? We are just referring to the standard neural scaling laws, isn't it? The neural scaling laws. One easy way that you can make a transformer more capable is just bring more data, bring more compute, and bring more parameters, and do it in a concerted way. There are particular equations, optimal way to scale all three together. If you do that, your model will become quite capable. We all know that. But what they say is that we find that scaling with flow matching, simple transformer-based models with flow matching. And flow matching is a work that was from Meta itself. And We will talk a little bit about flow matching after we have run through the paper. It's a very interesting technique. And I believe it's a generalization beyond just diffusion models. These days, diffusion models are very popular, and they instead use flow matching. Now, if you anybody who has background in normalized flows and flow matching, just show of hands. Otherwise, in any case, I'm going to explain this. It yields high quality generative models for video and audio. Notice the fact that they did not say diffusion. Do you notice that? Right? Whereas, to the best of our knowledge, other alternatives like Sora, etc., those are diffusion-based models. Right? These people did not use that. They instead said, just take a simple transformer, couple it up with flow matching, and you will generate high-quality models. But obviously, they have put a lot of effort to figure out how. And that's what this paper is about. So they have actually 4 models. One is and I'll just highlight those relevant parts. There's a 30 billion parameter. So I'll write it down, models. So they speak of a cast of models. So what are those models? Those models are, number 1, this is your movie gen video. This is a 30 billion parameter model, 30B model. What does it mean? Give it a prompt to this model, and out will come a video, right? Then they also have a movie gen audio model. And what this does is movie gen model 13B and 13B. This one is a smaller model, and input is into this. The input is a video, and it will infuse it with audio. So it is a video to audio. Interestingly, a video to audio. What it means is it will look at the video frames and it will infer what is the sound that goes with it. Quite remarkable. It's a 13 billion parameter model. Then they give you, so this is number 2. Then number 3 is a personalized version of number 1. With painting on a person's face with picture. So you can give it prompt, a picture, face. Both of these go in and will come a video, which is personalized with that person in the video, isn't it? That's your number 3. And then they have a 4th model, which is the movie edit video, movie gen edit. So this is also the same thing, movie gen, but with the edit capability, can edit a video. So in this, you will give a video, a prompt of what to do with the video, and out will come edited video. That's what this paper claims to do. So that, as you can imagine, there are quite a few accomplishments. I mean, theoretically, this could have been 4 separate papers in many ways. So movie gen audio. So we add video personal. So how do they do it? There is a whole process of training it carefully in broad strokes. They first train, like the first thing to ask is, how can you produce such high definition videos? So the way they do it is they start by training the machine with simple images, text to image. So you generate little images. You say, okay, that's not a big deal. You do that, but you use flow matching rather than any kind of a diffusion model. Then the second thing you do is that you go from text to image plus text to video pre-training. And also you upscale it a little bit. From 256, you go to 768. And then you also add sort of videos into the mix. So you slowly do it. And then you go and do all the other personalization, text to video, fine tuning, and video to video editing. So these are the steps that they take. Now, in this paper, the important thing that we will focus on is, and let me make this a little bit bigger. The first thing they do is we train a single joint foundational model, MovieGen Video, for the text to image and text to video task, which is important. They are not creating one for text to image and another for text to video. They are saying image is nothing but a video with a single frame. Are we together? So their statement is image is by definition a video with single frame and no sound. Right? That's all it is. So let's train directly for video. So it's a text to video of which text to image just happens to be a degenerate case. Given a text prompt as input, a foundation model generates a video consisting of multiple RGB frames as output. So as we know, videos are frames, right? So you will end up with lots and lots of frames. And it produces color frames as output. We treat images as a single frame video, enable us to use the same model to generate videos. Compared to video data, a paired image text datasets are easier to scale with diverse concepts, etc. So I won't talk, this is a very long paper, 92-page paper. So I will actually, I know that we have only about half an hour left. So I'll just give you in broad strokes what they do. This is a temporal autoencoder. We are all familiar with what autoencoders are, right? And temporal means because there is a time sequence, you have to bring that also in. Now, these days, when you do the encoder part, and actually of the temporal TAE, temporal autoencoders, only the encoder part. So remember, an autoencoder is like this, right? Typically, this is the picture you have. You have the encoder, decoder, right? That's how you think about it. But here they are saying, that's why they have this funny shape. We are looking only at the encoder. Now, how do you implement these days? There are only two mechanisms people can use to encode images. You could use CNNs, you could use attentions, right? VIT kind of thinking. And generally the state-of-the-art encoders, they use a mix of both, CNNs plus attention together within the image. But at the end of it, they will generate, what do they generate? Little feature maps or patches, right? You take that, and then what do you do? Suppose they generate a lot of feature maps, so you just flatten it out together. At the same time, you sample off a Gaussian noise, and you will see why you do that. You do that to give it, Gaussian noise is essential to bring it, or to give it certain ability to produce different results over and over again. Otherwise, it will produce the same thing. Right? So you sample off a Gaussian noise to change the result. This is something you must be familiar with. For example, if you remember your GAN, you sample off a Gaussian noise so that your output is different. Every time it generates a different face, right? For example, cycle GAN and so on and so forth. So this part is obviously understandable. You need to inject or sample off a Gaussian. Otherwise, how would you get your variety? Now, once you have this encoding, now what do? This represents your video. Now you need to, this is the stage where you need to bring in, a decoder. Typically, you would bring in a decoder. Except that before you bring in a decoder, you have, the decoder is your standard decoder. So here they're using Llama 3 video. So your decoders are typically, standard decoder, right? And again, a temporal autoencoders decoder part, but here they have implemented it using the Llama 3 video. But the interesting thing, the both expected part and the thing that to remember is you need to ground it in text, because here is the joint image and video generation pipeline. So what do? You are given this, and you have given a picture. So you're giving a video and the description of the video, right? Emu holding a sign says, "No movie gen is the best." No, movie gen is the best, right? So here's your emu. Now, one question is that how do you generate textual descriptions of videos? Right, and audios. Well, there are many models to do that. For images, of course, we know we can use Blip to Lava, whatnot, right, to generate textual descriptions. And then you can use Llama 3 video. You can use any sort of model to generate. So this kind of a paired data between image or sort of video and its text description is easy to get. Once you can have that, now you can feed it into train a decoder network. And once you train that, then what you have to do is you have to upscale. And so you'll see that this is the overall picture, but you will have to now what is happening here is you have a cross attention. You're passing it to a transformer. You're passing this encoding to this is the cross attention piece to the transformer, and then you're passing it eventually to the TAE decoder, right? So the transformer will do its transformations. What will it do? It will produce some logics. Those logics, you can feed it into the TAE decoder, the decoder part of the architecture. What will the decoder do? Decoder will then start producing the frames. But those frames will not be high resolution. So you need to upscale it a little bit, right? So now there are certain computational aspects in this paper that they go over. First is that, in the interest of computation, they do some compression and then they do some expansion. First is, so again, they mentioned that the temporal autoencoder it's a variational autoencoder. And as you can imagine, these have been known for quite some time, in 2013. Most of you know the theory of variational autoencoders. What are variational autoencoders? Variational autoencoders are encoders that insist on projecting your input into a latent space, where the data distribution is inherently Gaussian, right? Gaussian, latent probability distribution. Gaussian is like Bell Hill. In the latent space, or when you project all the input data, the latents form a Gaussian. Think of it like a Bell Hill of sorts, right? It's a Gaussian distribution. When you force that onto the machine, you say that you can't produce any kind of a latent. You have to, in other words, your loss term has the reconstruction loss and a term which is the Bayesian inference term, BI term, which basically measures the KL divergence between the distribution of your data, of your PZ, and a Gaussian. It says that your PZ must look like a Gaussian. Otherwise, you will pay a penalty in your loss term. And by forcing the machine to minimize that penalty, you essentially make sure that in the latent space, you have a Gaussian distribution of your latents. So that is something we have known and compare. So here's how we interpret this part. What is the shape of your data? You may have T prime frames, right? Let's say 10 frames in your video, 100 frames in your video. Then you have 3, and then you have height and width, because each video is made up of frames, right? Each frame has a certain height and a certain width. What does the 3 represent? The RGB channels, right? The red, blue, green channels of that. So it makes sense. What it is saying is that you compress the input video, space of the video, to a continuous latent X of this shape, T, C, H, and W, where the total number of frames that you keep is less than the original number of frames. The height is reduced the width is also reduced, right? And they'll say something about C. I forgot what they say about C. In our implementation, we compress the input 8x. In other words, the number of temporal frames or the temporal dimensions is reduced by 8, height is reduced by 8, width is reduced by 8. Right? So what they're doing is they're compressing the video before they're taking it through the whole process, TAE. Right? So the output of TAE, so in other words, the output of the TAE, this patchified version here, is much, much smaller. And this compression reduces the overall sequence length of that. You would expect what it is. Now the question is, how is this TAE implemented? Right? There's a little bit of technical detail of the TAE, which is straightforward if you are used to encoder and the decoder thinking. The only thing to know is that, see, suppose you start with, let's say, 64 frames, and it reduces you down to 8 frames, right? But let's say that you, or let's take a number, not 64, because 64 fits exactly. Let's say that you started out with 63 frames, and it reduced it down to, let us say, 8 frames. So when you decompress, or when you decode it, it will, 8 times 8 will become 64. So you have ended up with a fictitious frame, right? A non-existent frame in the decoder. Variational autoencoders, autoencoders are supposed to reproduce the input exactly, isn't it? On the other hand, you ended up with some extra frames. So what do? You discard those extra spurious frames, right? It's saying just discard the last few frames. And whatever remains is the output frame. That's it. So these are very common sense techniques that you use. Now, they also observe that in prior work that people have done, sometimes you see spots, little spot artifacts in the video. Let's say here, do you notice that? So this one, this little errors. The prior techniques used to have errors from other researchers. So they have a very simple way to eliminate it. They found what is the cause of this kind of a video generation, these blemishes in the video. They found that the errors come because these latents that you generate, the latent vectors that you generate, X, right? So you see that the X itself will have a certain distribution of values, right? What they are finding, or they claim, is that the outlier values here in the latent space of the latents, the outlier values of the latents, they are actually getting decoded as that trouble. And it makes sense, right? Because a machine would never really know. There isn't enough information to figure out what to decode it into. Does it look like a bear or a horse, or what is it, right? So what you do is that they say there is a very simple way to remove the outlier. You introduce an outlier penalty loss, which basically, now let's decode it and see what it means. What is this term? This is the departure from the mean. Isn't it? So suppose people's height, the typical height of people is 5 feet 8 inches. So you get a guy who is 6 feet 11 inches. Right? Now, you would say that guy is an outlier, isn't it? And how would you know how it's an outlier? One easy way is to say, look at the difference between these two. Compared to the mean, how much bigger is this person? And so this is the level measure of the departure from the mean. And then you ask, how much does it compare to the standard deviation? So sigma, right? So if you make a bell curve, and again, I'll just do this. If you make a bell curve, this is sigma. You realize that this is the mean, this is sigma. And the definition of outlier is what? Typically, you say something is an outlier if its value, if x minus mu greater than some either 2 sigma or 3 sigma. You can pick that. People's definition of outliers differ. Soft outlier is at 2 sigma and hard outliers are at 3 sigma. In their case, they just set it to three sigma, hard outliers. They say just remove the hard outliers. If you remove the hard outliers, it will solve your problem. The spottiness will go away, which itself is an interesting, little tiny little nugget that, okay, they figured it out and they fixed it. That's that. Next comes, there's more to it, but I want to come to the main objective, training objective. How do they do it? So this comes to normalized flows. Oh boy, it's already late. Let me see if I can give you an idea of normalized flow. And normalized flow is something that people find a little bit of difficulty understanding. So I'll read it out and then, flow matching and the whole theory of normalized flows and so on and so forth. So I'll explain what flow matching is. Flow matching is, I'll give you how about this? I'll start with a very intuitive picture. Right. See, suppose you have this, and let us say that you drop, you put a drop of ink somewhere. You put a drop of ink. Right? It's heavy here, then it's a little bit lighter. Something like this, right? So imagine a batch of ink. You just dropped a little bit of ink. Try this experiment in a beaker, and you can do that. Now you realize that suppose the water itself happens to be flowing. There is a water current in this direction. Something like this. Imagine that there is a current field, right? And guys, I'm trying to give you the intuition, a physical intuition into what all this is. A current, water current. The term that you use is it's a vector field. Why is it a vector field? Because at each point, there is a speed to the water, right? There is a certain, at any given point, there is a speed to the water. Would you agree? There's a vector that gives you how fast the water is flowing at that point. Make sense? And so you would agree that because this field is there, what will happen? After some time, little bit of time, your situation might be that this little drop has moved forward, and it is now, and it has spread out a little bit. It is looking something like this, isn't it? So each point here has moved to some point here. Are we making sense, guys? This is the flow. Yeah, guys, right? So suppose this is at t is equal to 0, and this is at time t, some time t. Right? This is time t is equal to 0, and this is time is equal to some time t. Would you agree that this would happen to your little dots of ink? And because this happens, oh, sorry, where's my thing gone? So this is it. The way to think about vector flows, it's a very physical intuition that in a water, in a flowing stream, there is a current. And there's a current, there's a velocity of water at each point. And so if you drop a bit of ink, like we have done, this blue ink, if you put it there, that blue ink will flow over time, right? And then if you look at it at the next even greater time, t prime, it would have diffused even more. It would have, let's say, gone completely off the screen. Like I'll make a bigger thing there. It might have gotten, because the field is sort of spreading it out, it might have become something like this, right? But you would agree that the flow position, where is that each point x is a function of time, right? Where is that point later? But that thing depends upon what? It depends on the vector field. right? In fact, the rate of flow, the rate of movement is quite literally the vector field. In other words, your vector field, Vt, is quite literally the movement of this point over time, dt. It is quite literally this. Does it make sense? Right? The rate of flow. And that is what, so when people talk about flows, these two things are coupled together. First, there is a vector field, and vector field causes a flow of points from over time. The points evolve, right? And the closest intuition that you can have is just think of ink being put in water, and the vector field is the water current. It will take it, it will spread it out. Or it will move it around in such way. If the vector field is converging, then of course it will all take it towards a sinkhole or something like that, whatever it is. So that's the meaning of this vector field. Now, why is this certainly relevant in this paper? It turns out that there is a whole way of looking at images and asking. So I'll give you the basic intuition because we have run out of time and I don't know how to summarize such a big, beautiful mathematics in a few minutes, but I'll do it just through intuition. See, what you're asking is this. You're saying, suppose I give you a Gaussian distribution. This is a this is a Gaussian distribution, right? And I say, from a Gaussian distribution, and I have data. So you have images, right? X1, Xm. You have some images. You ask this question that is there a way for me to sample a point from here and make it flow it into this image, right? So suppose this image, they're both in the same dimension. Let's say that this image is whatever dimensionality, d dimension. So you start with, you sample of X also a d dimension, but you take it from a normal distribution, a bell curve, a bell hill. Imagine a bell hill of d dimension, and you just sample a point of that. And now you ask this question where data is distributed like that. Now you ask this question, can I flow it into one of the images and generate it, right? And it's a very interesting thing. In some sense, you notice that you're going from pure noise, you're trying to get back to an image. Now the question is, how would you do that? Right? Now, as you do this, there are some very interesting bits of vector calculus that comes in. In particular, Jacobian comes in. See, so let me just write the word Jacobian. It comes in, it's beautiful. It's a determinant of Jacobians coming, but we won't get into too much, but let me see, how can I explain this math in a very intuitive way? So, okay, let me explain this. Maybe this is it. So this is it. See, guys, let's focus on this equation. Xt. What it is saying is, suppose my starting position is x0, right? Which is your basically noise, sampled of some point sampled of the Gaussian, right? And let's say that the final position is this, the actual image, some image, right? Some good image. Then suppose I am halfway somewhere in between. I am at a given, so at time t is equal to 0, at t is equal to 0, I'm here, and finally I'm here. Suppose I've figured it out, how to go from here to there, right? So you would agree that at some in-between time, x, actually, let me just say t is equal to 1, finally I'm there. So somewhere in between, my situation would look like this. I would be somewhere in between, right? I would be some proportion of, I would look somewhat, some proportion, I would still look like, let's say that this part is, I am, let's say, this close to the destination, right? I am 30%. Let's say, let's measure actual distances. Let's say that I am, this distance is 0.3, and this distance is 0.7. Right? One way of looking at this, if these are vectors, you could say that a simplified version is that I am made up of, this point is made up of 0.3 times x0 plus 0.7 times x1. Does that make sense? In some sense, right? To what proportion is it like that, right? Now, that is what this equation is saying. You notice that that's what we are saying, except that there is a minor modification. There's a technical term, 10 to the minus 5. You do it for some technical reasons we won't get into. But if you were to take this equation out, then it would look like what I'm saying. T times x1, that is how close are you already to the destination, plus 1 minus t. 1 minus t comes to like this is 0.7. So this has to be 0.3. 1 minus 0.7 times x0. So that's all we are saying. This is your linear. That's why this is called a simple linear interpolation. If you have this equation for your flow between starting point and destination, which is the simplest version that you can take, it turns out it works. Then obviously, to the extent that velocity is the time derivative of it, it is just this. Now you ask this question and the rest of that, denoting the model by a parameter. So suppose your model has so many parameters and text input. So what happens is that, let's say you have built a model, which now produces xt, but given what? Right? It has some prompts. Remember, this xt, it produces xt, but based on what? A prompt there and the time itself. Time has flown, right? Like you would agree that your predicted xt is this. Your prediction, let me, if I may use the word xt, predicted xt at that, or the constructed xt from the model is something like this. It has built it out of the input model, and it has built it out of the prompt, and it is a function of time. What do you want to make sure? You want to make sure, and this is, by the way, the velocity field, not the model. It is no, actually, I shouldn't say this was wrong. I apologize. This is your velocity field. In some sense, this is the predicted velocity, v hat. Let me call it v hat, right? Velocity field, predicted. If this is your velocity field predicted, and you happen to know the exact velocity field, which you do, then the question is, can you create a loss function out of it? That is easy. That becomes a simple regression-like loss, mean squared error loss, right? So in other words, if you have a model that's predicting a certain velocity field, a certain way that the water currents are moving, but you happen to know exactly how they are moving, right? Then you can create a loss function between these two vectors, and that is easy. That is your that's your standard regression loss between these two vectors, a mean squared error, and you can do it. So guys, I have glossed over a lot of theory, and I apologize for getting confused along the way. But it's the normal flow is a very beautiful idea, and the flow matching is a beautiful idea, and there's a lovely paper on it, which is quite detailed. Maybe we should do a paper reading on it at some point. But take it for granted that if you follow this, in some sense, this is many people believe is better approach than doing diffusion models. So they seem to be using this, or at least it's an alternative to diffusion. Let's put it this way. So now the rest of it is the architecture. How do they do it, and what do they do? And there's a lot of, and then obviously one of the things they do is once they produce images, they have to upsample. They have to do super resolution of the image. So they also have an upsampler in the story, which is not, I mean, it is good to have that. It is good. They bring in an upsampler and so forth. A little bit more on the scaling and attention and so on and so forth, given the input. So one of the things is when you do this, the amount of hardware they used was actually unbelievably large. It was at some page,
they mention it. Let me see, where do they mention it? I had it somewhere in the notes. And I remember that it was quite surprising, actually, that they use so much hardware. Yeah, they seem to mention it on page 10. Yes, right here. Look at the infrastructure that they used. We trained the media generation models using 6,144 H100s, right? Each running at 700 watt. This is your thermal envelope with 80 GB memory. Each of these videos had HBM stands for high bandwidth memory. So these are the state-of-the-art GPUs. You're using 6,144 of this. And obviously, they use all sorts of NV switches and all sorts of optimize. Nevertheless, they do all sorts of parallelizations. So it wasn't just a model building exercise, it was a feat of engineering, because they bring in, they use every opportunity to bring about parallelization to optimize the process. They did that. Right. So data parallelization, tensor sequence parallel, sequence parallel, and whatever they could do to model, you can see that, right? They did a lot. Now, one of the things they did is when they were training on long videos, they took little tiles of it and worked with that. Sometimes with overlapping tiles, I think, in the decoder part. So I won't go into the rest of it because we have run out of time, but that's the main idea. I would say that it's a remarkable paper, and the results, I suppose, just seeing the demo speaks for itself. I wouldn't go over the rest of it, but I invite you to play with the demos. Right? At one point, they point out how different or better it is compared to, for example, OpenAI Sora. Here is the image. When they compare it to Sora, the image that Sora generates and the image that the movie that their algorithm generates and the movie that Sora generates, obviously they want to, I mean, the claim is that it is substantively superior in this. So that was this paper. Again, to recap, it's a paper that does not use diffusion. If you remember Sora's approach, and a lot of the other commercial models are diffusion-based models. This model is a very simple, it says that you use transformers, you use autoencoders, variational autoencoders, temporal variational autoencoders, and you use a flow matching. So flow matching is, again, a paper that came out, if I'm right, from Meta itself. Flow matching, and together, which makes for a relatively simple architecture. And which is more interesting is you see a somewhat absence of hacks. Today, if you look at the way people do, for example, diffusion model, right? The typical diffusion models would be something like you take an image, you add a little bit of noise, plus noise, you get a noisier version of the image, right? So you have now, and then noisier. Finally, you have nothing but a normal. You can mathematically show that what you'll end up with is just noise at the end of it, which is common sense, right? You'll end up with Gaussian noise, nothing but that. But then what you do is you train the machine to, at each step, be able to reverse it, undo the noise, right? So that it learns how to inject some sort of a real world, a structure by denoising. So this was the sort of reverse diffusion process. What people do in reality is a lot of hacks. They sometimes go like this, straight to the end. Then from there, they'll come back, they'll do it. I don't know, if you look at the actual implementations, you'll see that they have become very, very sophisticated. There are a lot of clever tricks people use to get it done. In this one, as far as I can make out, they're not very clever tricks. It's a straightforward, clean architecture, all things considered. Obviously, not an easy one to build. You can imagine the tremendous amount of thinking and research that has gone into producing this, but it's really awesome. And the results really speak for themselves. So with that, I'll I will end today. Jorge, yes, it is, diffusion is the injecting the noise and reversing the noise. Whereas in flow matching, You don't do that. You don't train a model to undo noises. You instead teach it to go from a non-informative, in some sense prior, a non-informative point taken from a Gaussian and flow to a real image through a set of transformations. That's what you do. Mike, your comment, they all look contrived somehow. You mean those videos, is it? All
Yes,
right, guys.
sorry. Yeah,
Yeah.
sorry, it took me a second to unmute. Yeah, the videos, something weird about them. I can't put my fingers on it, but
Yeah, actually, we better learn or figure out how to tell them apart, right? The real from the fake, because it's getting harder and harder. I couldn't tell them apart. It just looks like, obviously, as a photographer, I know that you have to have, like, to create a real video like this is very, very hard. You know that without camera shake to get a video of a child running, which means that you're probably running with a gimbal. You know,
but
a gimbal to stabilize with a camera attached, and you're running with all your might behind the child.
see
So
how
it's
blurry
actually
it is?
Hmm?
See, it's very blurry to me. I see a blur. There's no fine details, especially in the sand and the
Yeah.
white shirt, like the yellow shirt and
Yeah. No, it does need some, obviously, more refinement because they have upscale. Remember, there's an upscaler that is just doing a super resolution in a lower resolution image. So yeah, I suppose you did catch on to the one thing that we should watch out for. Hopefully, that represents their scope for work. You're right. It is certainly not 4K resolution. It's high def. And that high def is achieved by upscaling. And that seems to be the thing. Actually, most of these video makers, video gens, they do use some upscalers, as far as I know. They produce low resolution videos and then they upscale it. That seems to be the state of the art at the moment.
the amount of hardware they took is astounding to generate these images.
Yes, it's a huge amount of hardware that has gone into this. All right, guys, any other comments or anything else before I? So I suppose this is an invitation to learn more about flow matching. Flow matching was a lovely paper, and obviously, when I, as a coming from a mathematical physics background, I totally love it because you get to see diffeomorphisms, shape changing, right? And see, to me, this is the way we would talk is that this particular shape is getting this shape is getting remolded to this shape, right? These are diffeomorphisms over time, right? And obviously, we love this sort of language, this sort of things, and vector fields. Vector fields gets people with physics background very, very excited. So it's really nice to see how much of physics is coming into gradually. But you know, the things that used to be in the domain of physics, I wouldn't say physics is coming, but theories or math that is more or less pervasive in physics, or mathematical physics at least, or quantum physics, is beginning to make its way or inroads into machine learning, into AI. Right? And not to mention the fact that the Physics Nobel Prize this year has gone to Hopfield and Hinton, right? Which is itself a great moment of celebration. Whenever I read Hinton's paper, I couldn't help remarking over the years how much of his intuition he deliberately borrows from statistical physics, statistical mechanics. So, and the atomic theory and so forth. So it's really nice to see this. Even the diffusion model, by the way, diffusion model comes from a non-equilibrium thermodynamics, right? So you have now two sets of models to do video generation, diffusion-based models, which come from non-equilibrium thermodynamics. In fact, the original paper was a title that introduced diffusion model, had the word non-equilibrium thermodynamics in its title. And now a flow matching itself uses things or arguments which are very sort of native to people with physics background. So it's fun. Yeah, hooray. Just to think that AI is just starting out. This is really amazing. It's fun. All right, guys, any more comments? Otherwise, I'll end.
Thank you, Asif.